All right. So here's where we are. Today is Tuesday, September 29th. We're going to start off with chapter 3 on exponential and log functions. Okay, so I'll take you back to your Algebra 2 days. Right? We're going to finish chapter 3 on Thursday. There's not too much for me to say, and I'll show you a lot of fun videos, but it's a matter of you doing the homework. I mean, you have to practice these principles, right? So I don't have too much to say, but there's some good homework to do, right? All right, and then chapters 2 and 3 are part of the big homework assignment, which will be due a week. A week from this Friday. So this will be due Friday, October 9th, and that should be well into my grading period. Finally, the month of October, right? So Friday, October 9th. That's when it's due, and we'll have our big question session on Thursday the 8th, and I'll have some time as well on Tuesday the 6th. And remember, I do record them on Zoom and then put them on YouTube unless students object. All right. Okay. So any general questions? Again, October is gonna be my big grading month. Today is when we start the my videos from spring. They're good videos. They are still good videos. My marks are a bit thinner, and that's okay because I have denser typeset, but the videos are still good. Let's see what else. Any general questions before we start? Any general questions? All right, lots of great videos today, by the way. Lots of fun videos. All right, so let's go ahead and start.
Hi, everyone. We're continuing with section 2.4 on complex numbers. But let's review section 0.9 on...
No, wait. Wait a minute. Let me see here. Oh, I see. Okay, I'm listed down here. Okay, but this was listed early on when you go to my YouTube site. But on my list, yeah, because remember, I'm wrapping back to my spring videos. So yeah, we're back here. All right.
Hi, everyone. Before we start the notes for chapter 3, I'd like to start with some fun and games. So I love being sick back in 4th grade because then I could stay home and watch my favorite game shows, including Card Sharks, which was something that really got me into math and programming because I programmed this bonus round I'm going to show you. Here's the opening ditty for this game show. The poems varied from episode to episode. The poems were mailed in by fans. This is on our classic game show channel, which you can subscribe to.
All right, now actually, what I can do is...
Hi, everyone.
Okay, so I can actually show you... so let me see here. Let's see.
Hey, everyone. This is Card Sharks on NBC.
Card Sharks, yeah. Okay, so I have the screenshots on my YouTube channel, but all right, I should pause. I should pause the video because I did do a collection of Card Sharks things here. I love Card Sharks. Okay.
So before we formally introduce the notes, let's have some more fun with exponential growth. Okay, so Card Sharks. Well, here's the deal. Cost of living is exponential, right? So here is a US inflation calculator. So this episode was taped in 1978. By the way, I should credit NBC for Card Sharks. Okay, so this episode was 1978. And let's say that Norma spends it all $28,800 on something, all right? Then the year 2020, how much would it cost? Let's hit calculate. It would cost over $114,000. So something that was worth $29,000 back in 1978, the equivalent of that would be over $114,000 in 2020. I'm basically saying that cost of living is exponential. All right, so on Mathematica, I did some basic calculations. An estimate for what $28,800 from 1978 would be today, American dollars, right? Now, inflation has not been constant, so it's not strictly exponential. Cost of living has not grown in a strictly exponential sense. But average inflation has been 3%. So as a rough estimate, let's assume that inflation has stayed constant at 3% per year. It's a very simplifying assumption, but it will help us with modeling and with estimates. All right, well, we get something close to the inflation calculator result. The inflation calculator said over $114,000. Well, okay, it's been 42 years since 1978, and this basic calculation says about $111,000. So remember, $28,800, that was the value in 1978, the cost of something, I should say, in 1978. Inflation, let's assume, is 3.27% annually per year. We'll talk about that. So this base year is 1 plus 3.27%, or 1.0327, raised to the 42nd, because the inflation rate we're assuming is 3.27% each year. So in terms of the cost of living deal, right, that's going to be exponential growth over those 42 years. So something that would have cost us $28,800 in 1978, assuming that the overall basic value stays the same. In pure money, it would cost us over $111,000 or over $114,000 today. Okay, now what if Norma had invested the $28,800 in the stock market before this latest crisis hit? Well, at least before this latest crisis, the stock market has grown on average about 8% per year. Of course, it's had its ups and downs. We've seen that. But as a simplifying assumption, let's assume that the stock market has grown 8% per year, just simplistically. Well, we start with $28,800. Let's say she invests it. 8% growth. 1 plus 8% is 1.08. See, we need the 1 there, because if we didn't have the 1, then she wouldn't be growing, she'd be shrinking. she basically would lose money with each new year. Okay, so she's growing. We have 1 plus 8%, 1.08. Every time another year elapses, we multiply by 1.08. She's growing, growing, growing exponentially. Okay, lo and behold, at least before this latest crisis, she'd have over $729,000. All right. If you want to, now here, let's model what she did in the actual game show. All right, so she started off with $200, and she basically doubled down. She was getting twice as much money with each new turn of the cards. So every time there was a turn of the cards, X increased by 1, and that leads to a doubling of her current bank account on Card Sharks. Now, I do realize that she got a bump of $200 in the middle. Let's ignore that for now, although that would be beneficial to us if we cared about our money. Okay, well, this is the curve that we get. Y equals 200 times 2 to the x. You can barely see the 200 down there, right? So she starts off with $200. This is a smooth curve. Technically, it's really dots or points. It's really a geometric sequence, which we'll talk about in chapter 9. But let's smooth it out, and let's say it's this exponential curve. Y equals 200 times 2 to the x. It's a J curve, a J graph. Science professors, chemists, physicists love to refer to these things as J curves or J graphs. And as you can see, by the time it came to the 7th turn of the cards, she turned over 7 cards, remember, okay? This thing predicts that she would be making over $25,000. Again, remember, she got a $200 bump in the middle, so she actually made a bit more than $25,000. But pretty good job of modeling, and it's this J curve, very rapid growth. When we hear of exponential growth, we think very rapid growth. And ladies and gentlemen, yeah, it's been in the news. Coronavirus, not so fun. Not a game.
Now, this was back in March. Remember, this was one of the first videos I made after the lockdown. So this has historical significance. See, so it's a March 11th article.
So here's an article by Tomas Puello from March 10th. Coronavirus, Why You Must Act Now. I'll try to send a link for this. So he has some interesting pictures here. Okay, Let's assume they're correct. Okay. Look at this. Coronavirus cases per country. South Korea, kind of a J. By the way, here's January 22nd over here. Here's March 7th over here. Look at this. South Korea, Italy, Iran, 3 countries very hard hit by coronavirus. Kind of J curves there, very frightening. We don't want J curves. We want to bend the curve, bend it down. We want to bend these curves down. And let's hope that in the United States, we won't have to deal with these kinds of J shapes. South Korea actually has done a lot to combat this. Italy even, at least it may have reached an inflection point where the number of new cases at least has declined. So maybe it's reached an inflection point and the curve will bend down a bit. So there is real application to what's going on nowadays. In the next video, we will start the notes on chapter 3 on exponential.
Yeah, sadly ironic. I know. By the way, as another example of, we're talking about big numbers, right? Like how much Norma made. I want to ask Google a question. I've done this before. Hey, Google, how much is Jeff Bezos worth? Not that you're worth always what your dollar amount is, but wow, look at that. About $175 billion. Also up there, Bill Gates, $115 billion. Elon Musk. You know who Mackenzie Scott is? Do you know who Mackenzie Scott is? She used to be married to Bezos. She's number 4 because she was married to Bezos. Then, he cheated on her and she got that divorce money. Okay, but hey, 57 billion. Yeah. Anyway, let's go on.
Hi, everyone. So chapter 3 deals with exponential and logarithmic functions, log functions. Those are the inverses of the exponential functions. So in section 3.1, we're going to talk about exponential functions and their graphs. Remember, as functions, they follow the same rules as in chapter 1 for functions in general. Okay, so let's start with the legend of the chessboard. This one might sound a bit familiar, although I've modified it and updated it from the Middle Ages. The original story takes place in the Middle Ages and involves grains of wheat. Instead, we shall transport ourselves to the distant realm of Seattle, where a smart programmer is haggling with King Bill. And we want King Bill's money. The programmer agrees to work for King Bill for 63 days, starting tomorrow. Today is day 0. So after seeing a large chessboard engraved into King Bill's floor, the programmer comes up with a scheme for his salary, or her salary. For now, the programmer tells King Bill to place a check for $1 on square 0 on his chessboard. All right, so here's $1 on square 0. All right. With each new workday, King Bill is to place twice as much money, a check for that much, on the corresponding square as the day before. The chortling King Bill, who has forgotten all of his math, agrees. What's going to happen? Well, I think you know what's going to happen. So on day 0, we get a down payment of $1. Laughable. But then on day 1, a check for $2. On day 2, a check for $4. On day 3, a check for $8. Doesn't seem too impressive at first, but here's the deal. On square X, the check you get is 4, in American dollars, 2 to the X. So, for example, 2 to the 3rd is 8. 2 to the 3rd is 8. So we get $8 on square 3. But watch how it grows. How much are we going to make on square 7, for example, at the end of the row? Well, let's take a look. I guess I better erase these here.
You can see I'm experimenting.
Eraser.
Yeah, this is like the Zoom thing. The annotation, annotate on Zoom. Annotate on Zoom.
Okay, so let's check out this table. On square 0, we have $1. Square 1, 2 to the 1st. Remember, we're talking about 2 to the X. I'll use this here. Right. 2 to the X in American dollars. Right. 2 to the 2nd is $4. 2 to the 3rd is $8. 2 to the 4th is $16. All right. By the time you get to square 7, see, we're doubling down, doubling down. By the time you get to square 7, hey, look at this, $128. Not bad for a day's work. On square 10, it's over $1,000. And every time you advance 10 days or 10 squares, the multiplier is over 1,000. On day 20, over 1,000, which is over a million. On day 30, over 1,000 times a million, that's over a billion. Day 40, over $1 trillion. Even Jeff Bezos couldn't afford that. By the way, how much is Jeff Bezos worth?
Yeah, I did this before.
We've had ups and downs in the markets, but he's worth about $114 billion. Well, he'd be broke by the time we reach.
Wow. Did you notice that? He's worth 175 now, huh? Wow. He's made a lot of money during the virus.
Well, the divorce didn't help either. Okay, anyway, so by the time we get to square 63, it's going to be over $9 quintillion, 9 times 10 to the 18th. That's the amount of money on the final square over here, day 63. All right, so on day 63, what's the value of the check? No one can write this check. It's that in American dollars. No country could write that check. In scientific notation, it's over 9 times 10 to the 18th. It's over a 9 followed by 18 zeros. It's a 9 followed by 18 digits. It's massive. All right. Now, in case you're curious, the total value of the chessboard is going to be 1 less than the amount of money that you would have gotten on the next square. So for example, remember that you're slated to get $16 on square 4. If you do the math, you've collected a total of you will have collected a total of $15 on these previous squares over here. So the amount of money on the next square is 1 more than all the money on the previous squares. All right. So the money that you get for the money you get for the whole chessboard, I should say, the money you get for the whole chessboard is going to be 1 less than 2 to the 64th. What is 1 less than 2 to the 64th? What's the total value of the chessboard? It's about twice that. It's about 2 times 10 to the 19th. Again, massive. So the overall value of the chessboard is twice the value of the check here, minus 1. We're talking huge, huge numbers. Even Jeff Bezos couldn't afford things. He'd be bankrupt by square 40. So we're talking about exponential growth here, okay? When people talk about exponential growth, hey, we started with $1, but that dollar can really grow. Exponential growth is usually taken to mean very rapid growth. Look at these numbers. We start off pretty humble, but then they get astronomical. Okay, so in our next lesson, we're going to talk about the math underlying all of this and the graphs. So I'll see you in the next video.
All right, any questions? Any questions? Kind of introducing exponential functions. They're interesting. Yeah, today's very interesting. Besides the debate.
Hi, everyone. So in the chessboard example, we were talking about a function that looked like that. F of x equals b to the x, where b was 2. We were really talking about 2 to the x, the amount of money on square x of the chessboard. But that's just one of many exponential functions. 3 to the x, 4 to the x. These also represent exponential functions. 2, 3, and 4 are nice bases. Now, that's not an official term. We call b a nice base, or I call b a nice base, if b is positive and not 1. Then it is a legitimate base for a legitimately exponential function. F of x equals b to the x, where b is nice. We'll discuss these problem situations later on. All right, so let's take a look at the graph of this. How do we graph y equals to the x, our payment function from part A? All right, let's go to Desmos. Okay, so we can ask Desmos, what does y equals 2 to the x look like? And it's that J curve, all right? 2 to the 0 is 1. Okay, 2 to the first is 2, 2 to the second is 4, and so forth. I'll plot those points. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Remember, y equals 2 to the x, right? And these are points on the J curve. Now, you can use the wrench here to change the scales on these axes. Right now, the scaling is equal on the two axes. Visually, you can make this look very different if you use different scales. Like, for example, what if we went from negative 100 to positive 100 on the y-axis, right? Then it would look a fair bit different. Okay, so the scaling does matter. All right, actually, let's go back to the original. Let's go back to equal scaling. Okay, so let's say negative 10 and 10. Let's go back to equal scaling. All right, well, here we have y equals 2 to the x. All right, here's y equals, well, here's y equals 3 to the x. Oops, 3 to the x. Y equals 4 to the x. These are all J curves, all right? In fact, y equals 1.1 to the x. That's also a J curve. It grows more slowly than the other guys, but it is ultimately a J curve. It really is a J curve in the long run, all right? So as long as the base is more than 1, you're going to get this J curve behavior, all right? Now, if the base is 1, that ain't exponential. That green line, that's not exponential. 1 is not a nice base. But if the base is a constant, a number greater than 1, then you're going to get a J curve. Even 1.1, y equals 1.1 to the x, that still gets us a J curve, especially in the long run. Okay. Now let's talk more about this J curve. So I'm going to clean this up a bit. Okay, and let's zoom back in. All right. So let's say that we have y equals 2 to the x. All right. Well, we know that 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. All right. But what about to the left of the y-axis? All right. What is 2 to the negative 1? Right. What is 2 to the negative 1? 2 to the negative 1 is 1/2 or 0.5. Remember that? To the negative 1 is 1/2 or 0.5. So when we plug in negative 1, we get 0.5 or 1/2. And we get this blue point over here. What about 2 to the negative 2? 2 to the negative 2 is 1 over 2 squared. It's 1/4, right? If you don't believe me, here are my notes, right? Okay, you plug in x equals negative 1. 2 to the negative 1, you're replacing x with these numbers. 2 to the negative 1 is 1/2. 2 to the negative 2, remember, you're plugging into the exponent, not the base. 2 to the negative 2 is 1 over 2 squared, or 1/4. If you plug in negative 3, 2 to the negative 3 is 1 over 2 to the third, or 1/8. All right, so let's plot those points. Plug in negative 2, you get 1/4. And if you plug in negative 3, you get 1/8. So we're doing point plotting here. Okay, so notice all these points lie on the graph. We have the appropriate function values over here. So notice that as the x-coordinate gets more and more negative, the y-coordinates, the function values, appear to get closer and closer to 0. And by the way, yes, that is an HA. It's a line, a horizontal line, that this graph approaches. But the HA is only relevant to the left, not to the right. Exponential functions are not rational. Remember, rational graphs, if they have an HA in one direction, you have to have the same HA in the other direction. This exponential function is not rational. It does not abide by those rules. It can have an HA in one direction, but it's an HA that's not relevant in the other direction. In fact, this function, this graph, explodes out here. Okay. So notice that as x approaches negative infinity, it appears that 2 to the x is approaching 0. Remember, we define asymptotes using ideas of limits and infinity. Okay, so the graph basically looks like that. In general, if b is greater than 1, then yeah, you're going to get a J-curve. So you're going to have many of the same features of this. So think for a moment. What are some features that are going to be common to all of these graphs? All right, so I'm just going to go back here. All right, take a look at this. Y equals 2 to the x, y equals 3 to the x, even y equals 1.1 to the x. What are some things they have in common? Think in terms of intercepts, domain, range. Intercepts, domain, range. And I'll see you in the next video.
So think about that for a moment, okay? In fact, I'll give you some time. Maybe 20 seconds or so. Intercepts, domain, and range for all these. All right, let's proceed. Oh, okay, I'll put this on.
Hi, everyone. So let's look at the properties of these functions and their graphs. So we have y equals 2 to the x in red, y equals 3 to the x in blue, even y equals 1.1 to the x in green. So let's talk about their features. First of all, let's talk intercepts. Y-intercepts. What can we say about y-intercepts here? Well, take a look. The point 0, 1. That magical purple point is the y-intercept for all three of these graphs. In fact, for all graphs for y equals b to the x, where b is nice, the y-intercept will be at 0, 1. What about x-intercepts? Well, turns out there are no x-intercepts. Now, you might be confused about what's going on here. Let me assure you, these graphs are not touching the x-axis. They get very close, but they're not touching. For example, 2 to the negative 10th is very tiny, but it's not quite 0. In fact, on the x-axis, we have a horizontal asymptote, an HA, at y equals 0. Okay, so we have one y-intercept at 0, 1 for all three of these graphs, and we have the x-axis, y equals 0, as an HA for all three graphs as well. Now, what about domain and range? First, let's talk domain. Domain, think x. We pick up every real number as an x-coordinate for each of these graphs. The domain is all real numbers. Now, you might wonder, what's 2 to the pi? Well, it is 2 to the 3.14 blah, blah. It's a calculus idea. But the domain is, in fact, all real numbers. The range, however, think y. Well, we're not getting all real numbers. We're only getting positive real numbers. So the range, as you can see here, the range is going to be, we think, the set of all positive real numbers. The range is the set of all positive real numbers. 0 is not in the range. Remember, there are no x-intercepts. Y is never 0 on any of these graphs. 0 is not in the range. Okay, so for all of these graphs, all functions of that type, we have the same features. In general, if b is greater than 1, remember that means we have exponential growth, right? The graph of f of x equals b to the x, where, again, b is greater than 1, will resemble a J graph, okay? All these J graphs fall in that category. Basically, y equals b to the x, where b is greater than 1. And we have these as common features for all four of these functions, okay? So the domain is all reals, right? We get all real numbers as x-coordinates. The range is the positive reals, okay? The y-coordinates we get are the positive reals. The x-axis is an HA. It's a line that these graphs approach, and it turns out they never touch. That's why 0 is not in the range. By the way, in trig, we're going to mention that you're actually not forbidden from touching an HA. So it's not true that graphs never touch their HA, but it's true that for fairly basic graphs, they tend not to touch their HAs. And these guys do not touch their HAs. In trig, however, I'll show you at least one graph that will touch its HA. All right, the y-intercept is at, again, it should be 0, 1, 0, 1. Type that in, 0, 1. That's the y-intercept. Remember, we tend to prefer ordered pairs for our intercepts. Okay, so those are the features for f of x equals b to the x, where b is greater than 1. But what if b is, say, 1/2 or 1/3? What happens? All right, well, actually, we could play a little game here. All right, what if b is strictly between 0 and 1? For example, what if b is 1/2? All right, let g of x be 1/2 to the x. This is actually related to f of x, which was 2 to the x. Think transformations. We did this back in 1.4. So if f of x is 2 to the x, don't freak out, but I do want to discuss why this graph's going to make sense here. All right, so observe, f of the opposite of x will be 2 to the opposite of x, and you can actually factor this exponent, and it looks like this. 2 to the -1, all to the x, is 2 to the -1x. We're reversing the rule that says that when you raise a power to an exponent, you multiply the exponents. But what is 2 to the -1? It's 1/2. 1/2 to the x is then g to the x. This guy here, the guy we've been talking about all along. So what's my point here? I'll change the color to really emphasize this. Let's go to blue, all right? So what we have here is that if you replace x with its opposite, all right, you're going to get the guy that we want here, 1/2 to the x. So what happens if we go from the graph of y equals 2 to the x to the graph of y equals 1/2 to the x? What happens? Choose a different color. Okay, so here, this is the graph of y equals 1/2 to the x in purple. How do we get from the red graph to the purple graph? We reflect it about the y-axis. Remember, what we're basically doing is we're going from 2 to the x to 1/2 to the x. What happens when we go from 2 to the x to 1/2 to the x? We're basically replacing the x with its opposite. We're replacing the x with its opposite. When you replace the x with its opposite, when you're looking at y equals f of opposite x, you're reflecting the graph about the y-axis. Hopefully you remember that from 1.4. Now, if this analysis creeped you out, don't freak out. The key thing to remember is that when you're graphing y equals 1/2 to the x, you're getting this guy here, like a curvy L. This is not exponential growth. It is exponential decay, like radioactive decay. What's the idea of radioactive decay? The idea that if you have a radioactive material, like Stewie Griffin from Family Guy, let's say that the half-life of some element is 1,000 years, and you have 1 gram of it right now. In 1,000 years, it will decay to 1/2 of a gram. That's the idea of half-life. The idea being that the element will decay over time and approach nothing.
Okay, folks, I can't resist. I got to do this. This is a long video, huh?
All right. So again, here's the graph of y equals 1/2 to the x. But there are other graphs that look similar. So here's y equals 1/2 to the x. All right. Here's y equals 1/3 to the x. Again, it's this curvy L, exponential decay. Okay. Even y equals 0.1 to the x, right? Exponential decay. Actually, that's not so surprising. This might surprise you. Y equals 0.9 all to the x. Yeah. Now, 0.9, that's a pretty big base relative to these, but still, 0.9 to the x, exponential decay. In the long run, you're seeing exponential decay. Even y equals 0.99 to the x, again, exponential decay if you zoom out way out enough. So if the base here, the constant base, is less than 1, even a little bit less than 1, but stays positive, then y equals b to the x will be this curvy L guy. It would be shaped like a curvy L, exponential decay. All right. So in general, if b is a constant, strictly between 0 and 1, then the graph of y equals b to the x will resemble the curvy L graph that we see above. And yet, when you look back at these features that we saw for this previous case here, where b was greater than 1, still, domain is all reals, range is only the positive reals. I'm going to zoom in. I'll just do this here. I'll get a new screen. Okay, y equals 1/2 all to the x, all right? So again, the same features apply. Domain is all reals. The range is the positive reals. We have a y-intercept at 0, 1. No x-intercepts, although we do have an HA at the x-axis, or y equals 0. All right, so actually these same 4 features apply even if b is, say, 1/2. All right. Now some comments about bases that are not nice. What if b is 1? Well, 1 to the x is 1. That's just a constant. That's a flat line. If b is 0, 0 to the x is basically 0, although 0 to the 0 is weird.
I should have said when x is positive, because as I'll say in a later video, you got a problem if you have x being -1. I'll say that in a later video.
Again, it's basically a flat line. So these do not represent exponential functions. They're basically constants. If b is negative, we have a real problem, literally. So, for example, this over here. -2, let's say that's our base b, it's not nice. If that's raised to the 5/2, ultimately, because of this thing, the 2 over here, you're taking a square root. And, well, right now we have a problem if we have the square root of a negative number. So this is not even a real number for this value of x up here, the 5/2. So if your base is negative, you literally have a real problem, and I won't mess with you in that sense. So these bases will not give you exponential functions. Now, there is a base that we absolutely love. Our favorite base is represented by a letter. Its name is E. E is, of course, the 5th letter of the alphabet, but it's also a number. E represents a number. It's about 2.718. Both E and pi are pretty close to 3. And like pi, E is also an irrational number. There are various ways of defining E, many ways of defining it in calculus. For example, here's a limit definition for E from calculus. So E is the limit of 1 plus 1 over n all to the n as n approaches infinity. In fact, we could try looking at the calculator function here. Okay, y equals 1 plus 1 over, let's say, 10, all to the 10. Okay, this is of the form y equals 1 plus 1 over n, all to the n, okay, where n takes the value 10, all right? You can see it's about 2.6. What if we make n equals 100 here and here? About 2.7. How about 10,000 here and 10,000 there, right? About 2.718. So this is very, very close to E. So if you let n approach infinity down here and up here, then this number here will approach E. Again, E is about 2.718. That's pretty much what we're getting here. Now let's consider the graph of y. Well, this is so close to E, we may as well call him E. X of 1, or 2.718, shall we do that? Oh, graph it, yeah. Yeah, y equals E, it knows E. Okay, so that's a constant, y equals a constant. Take a look at this. Y equals this function of n, or x, as the case may be. Graph that. Hey, look at this. As n approaches infinity, right, then the y-coordinates the value of this thing over here, this whole thing over here, is approaching E. Okay. So this is an HA. Y equals E is an HA for this as n approaches infinity. That's one calculus definition for E. We love E for all sorts of reasons. A key reason is that the derivative of e to the x is e to the x. By the way, e to the x gives us the natural exponential function, and e is referred to as the natural base. E is our favorite base. In information theory, computers are supposed to be base e, really, and they actually experimented with base 3 computers, but base 2 won the day, binary. Anyway, what about the graph of y equals e to the x? Well, we've seen these things before. Here's y equals 2 to the x. Right? Here's y equals 3 to the x. Remember, e is about 2.7. Y equals e to the x. Okay, it's this blue graph that's between the red graph and the black graph. E is just a number. E is just a number. It's about 2.7. So y equals e to the x graphs as a J curve. All right. Exponential models, that's a fancy way of saying that we're going to attach this constant, like a coefficient. Basically, if you remember Norma from Card Sharks, she started off with $200, right? And that's going to be the constant A. In fact, A here represents the initial value, the value of this function rule when x equals 0. If x is 0, remember, this is 1, and then we're left with the coefficient here, 200. So A is going to be the initial value, the value of this when x equals 0. It's the initial value for this function over here. Kind of like time 0. What's the population at time 0? All right, so if b is greater than 1, oh, by the way, let's assume a is positive for now, and b is a nice base. If b is greater than 1, then we get a J graph, and we obtain exponential growth models used in applications such as population growth, like the Malthusian model. And we'll talk about that. Also, compound interest. We'll talk about that in the next video. By the way, Malthus was one known for giving economics the name the dismal science, because people were afraid that population would grow exponentially while food supply would grow linearly. That was a big fear. And Malthus was an economist who was concerned about that. If b is strictly between 0 and 1, like if b is 1/2, then you have applications like radioactive decay. Or imagine a store going out of business. Sadly, nowadays, many stores are going out of business. But imagine a store where they're cutting prices in half each week. Okay, then the prices will approach 0 very quickly. So these are exponential models. This is the form of a basic exponential model, and we're going to apply that to compound interest in the next video.
Okay, now, in the meantime, I would like to show you
Hi, everyone. We're continuing and finishing with 3.1 on exponential functions. So here, a key application with money, compound interest. The idea that interest can be paid on interest. So let's consider a banking account with compound interest, where P is the principal deposited in dollars. That's the amount of money that you put in the bank or that you borrow in a loan. R is the annual interest rate, but in decimal form. So for example, if it's 6%, you want to use 0.06, not 6 in the formula. N is the number of compoundings, that is the number of times interest is paid per year. So for example, for annual compounding, N is 1. For quarterly compounding, N is 4. For monthly compounding, N is 12, and so forth. T is the time elapsed in years since the deposit. Okay, I'm assuming that we're operating in terms of years here, like the annual interest rate. All these must be positive in value. So, good news and bad news. The bad news is that the formula looks like this. The amount of money you have after T years, assuming that you haven't withdrawn anything or deposited anything more, and assuming the interest rate stays the same. Of course, that's not guaranteed in real life. But there's the formula for compound interest. The amount of money you have after T years, or T years after the deposit, is P, the principal, times this thing over here. Now, you might be going, what does this have to do with exponential functions? Well, this is of the form of that basic model. F of t equals A times B to the T. This is horrible, sorry. Maybe I should type this. Okay, it's of the form A times B to the T. That's a little bit better. Okay, because the deal is that actually this is of the form a number times something to the T. So this is exponential in T. Now again, the bad news is it looks like this. The good news is that on an exam, I would never have people memorize this. Okay, now in case you want a brief explanation as to why it's exponential, I think I do have it somewhere here. No, okay, so the reason why it's exponential is that this here, 1 plus r over n all to the n, got to be careful there, all right? So this is of the form a times b to the t, where b is this guy in here, right? So this is exponential. Okay. As opposed to simple interest, where that's just the principal plus, and then the amount of time times the interest rate times the principal. That's linear in T. That's if interest is applied to the principal, but not on any further interest. That's linear in T. Okay, so example. We initially deposit $10,000 because we found it under our couch cushion. We deposit $10,000 in an account that earns 6% annual interest compounded monthly. Monthly, that means n equals 12. You should know that. How much money will be in the account after 5 years? That is exactly 5 years after the deposit, and I'm assuming that things are happening right after the moment you get the interest. Because technically we're talking about dots. We're technically talking about geometric sequences here, but we're smoothing them out. And we're also assuming that no withdrawals or deposits are made in the meantime. Okay, so the deposit is $10,000. That's P over here. Well, do that. That's P over here, all right? The interest rate is 6%. Remember, that's got to be converted to a decimal, 0.06. 5 years, 5 years. If this were in months, you would convert to years because we're talking annual interest. All right, we use the handy dandy formula, all right? But there's a warning that I have to give you folks. And I think I'll show this to you in Word. Let's show it in Word. Okay, so what if we have something like this? Okay, let's say that we have 2 to the 3 times 4. I should write it like this. 2 to the 3 times 4. Type it in like this. And then I'll superscript it, all right? Let's say that I owe you this in American dollars, okay? Okay, now what is this in reality? Well, it's going to be 2 to the 12th, because 3 times 4 is 12. Let's superscript that. 2 to the 12th, which is $4,096. Okay, 2 to the 12th is 4,096. Remember that 2 to the 10th was 1,024. Remember that from the chessboard? So that's the check on square number 12. It's $4,096, a hefty paycheck. So on your calculator, if you put 2 exponentiation 3 times 4 equals, would that give you 4,096? Try it. I dare you. Try it. No, it doesn't. Because what comes first? What comes first is this. 2 to the third is 8. And 8 times 4, that's a measly $32. Not that I would spit on $32, but it's not $4,000, right? So clearly, there's a big deal here, a big difference. Now, what should you do in your calculator? Maybe use grouping symbols? Grouping symbols are so important. Grouping symbols around the 3 times 4, and that'll get you 2 to the 12th or the 4,096. Or perhaps more easily, you can figure out that 3 times 4 is 12 and just figure out 2 to the 12th. That's probably more straightforward. But in any case, you have to make sure that you're processing this correctly. And I must say that when I was a TA at UCSD, this was perhaps the most common error I saw students make on their graphing calculators. Anyway, going back to here, all right, the exponent is n times t. Okay, we're plugging in, right? P is 10,000. 1, we need the 1 there because when interest is applied, you keep what you have so far. The bank doesn't take all that money. Otherwise, that's a total ripoff. Okay.
I better, I'm going to pause for a moment. Okay, so in case you want to write that down, 10,000 times, and then 1 plus 0.06 over 12, all to the 12 times 5. Okay, I know the captions are covering it up.
That was kind of like what I talked about before with Norma investing in stocks, right? The base or multiplier was 1.08, not 0.08. Likewise here, it's 1 plus r is 0.06 over n is 12, and then the exponent is 12 times 5. That's 60. So you might want to process that first. Okay, work it through. About $13,488.50. Okay, in fact, I'm going to do this. And this is going to stay on the screen. 13,000, whoops, 400, well, you know what? Let's type it. Let's type it. All right, $13,488.50. All right. And we're going to compare that with another scheme later on. Anyway, so after 5 years, after that interest is paid, exactly 5 years after you deposited your money, and you deposit your money right after a compounding period, $13,488.50. So you made a profit of over $3,000 over your $10,000 principal. Pretty good, very good. Okay. So now, moving on. See, this is going to be a ghost that we're going to compare to over here. Right? Continuous compound interest. What happens if we let n approach infinity? So remember, annual compounding, n equals 1. Quarterly compounding, n equals 4. Monthly compounding, n equals 12. Now, what if we go on? What if we have compounding once every day, daily, every hour, every minute, every second? Now, remember how the formula worked. The idea was that if you had more compounding periods, then the interest rate was basically broken up among the n compounding periods. So if you let n approach infinity, it doesn't necessarily mean you make infinitely many dollars because you're getting a smaller and smaller piece each time. All right. So P is the principal still, R is the annual interest rate as a decimal, T is the time elapsed in years, but no talk of N because we're letting N approach infinity. We're going to implement that. And when that happens, well, good news, bad news. Good news is we get a much more beautiful formula. The amount you have after T years, and it's continuous compounding, so we don't even have to talk about when is it relative to an interest payment. A equals PE to the RT. Good news is, it's beautiful. The bad news is, I would have people memorize this. PERT. It's basically PERT in dollars. Now, the reason why we get that and you don't have to know this. It's from a proof. So there's a proof in my notes that explains how when you take this thing and you let n approach infinity, then you end up with that. Now, this may recall something I brought up earlier. It was a definition for E. Remember this? E, that was the definition we had for E, and we're actively implementing that in the proof. So in case you're wondering why the E turns up, it's because of this thing over here. All right, PERT. So let's apply PERT. So everything else is going to be the same, except here we're going to talk about compounding continuously, as opposed to monthly, like before. So once again, we initially deposit $10,000 from under our couch cushion. We deposit it in an account that earns 6% annual interest compounded continuously. Remember, this was our result from compounding monthly, and we're going to compare. How much money will be in the account after 5 years if no further withdrawals or deposits are made in the meantime? Will we get infinitely many dollars? Remember, I said the answer was no, it's not infinity. But is it much more than this? How much better is continuous compounding compared to monthly compounding? All right, well again, P is $10,000, R is 0.06, T is 5 years. Plug these things in. Watch out, 0.06 times 5, you may want to process that first. You get 0.3, and then your calculator goes straight through, and we get,
I might want to pause this for a moment. You look at that calculation, right? 10,000 times e to the 0.06 times 5, process that, you get 0.3.
Turning to this now, we get 13,000, it's like the price is right, $13,498.59. The difference is $10.09. That's a DVD or something, right? So continuous compounding does not do us that much more favor than monthly compounding, actually. Even though we're doing something like every month, every day, every minute, every second. Well, yeah, but the interest rate's being broken up more and more also. In fact, if you were to compare it over a long time frame, I did this on Mathematica, right? Comparing monthly compounding versus continuous, right? Even over a time span of 450 years or so, about 450 years, comparing monthly compounding in purple versus continuous compounding in brown, not that much of a difference. Okay. Enormous scale here, but relatively speaking, not much of a difference. You can barely tell the difference. So continuous compounding, although it is the best of the various schemes, annually, quarterly, monthly, continuous is the best. Well, you don't get infinitely many dollars. It's the best, but there's a limiting factor. E gives us a limiting factor. All right, so that's section 3.1. Next up, section 3.2, log functions, the inverses.
All right, now actually, we have some time for some fun videos and a few more comments. Right, let's explain that.
Hi everyone, just a couple comments on 3.1 before we go on. Now, 0 to the x, that's 0 if x is greater than 0. Because 0 to the 0, again, is messed up. And even if x is negative, for example, if we have 0 to the negative 1, that's a problem because 1 over 0 is undefined. Another note which will come up in calculus, why do we love e to the x? Well, for example, the derivative function of this e to the x guy is itself. That's not true of, say, the 2 to the x function. So the derivative of e to the x is e to the x, but the derivative of 2 to the x is 2 to the x times ln of 2. It's a bit different. So e to the x has the property that the derivative, which we sometimes denote by y prime, is equal to y, the function value itself. The slope is equal to the y coordinate. So for example, if you graph y equals e to the x, right, here is the point 0, 1. The y coordinate of this point is 1, y equals 1. The tangent line turns out to be the line y equals x plus 1. That's the equation of the tangent line. It has slope 1. So y equals e to the x has the property that for each point on the graph, the y coordinate is equal to the slope of the tangent line there, which is a cool property.
Okay, so let's go ahead and take a break now, and then we're going to come back and do logs, okay? So I have 814. All right, I have 814. Let's break until 825, all right? So come back at 825. Oh, let me... Hi, everyone, we're back. Any general questions before we start logs? Any general questions before we start logs? Because I would like to start with a little song. They're going to reboot this series pretty soon, I think. And this is from Ren and Stimpy. Oh, I better pause for now. All right.
Hi, everyone. Let's start section 3.2 on logarithmic or log functions and their graphs. A key thing to remember is that logs are exponents. Logarithms are exponents. Let's say we want to evaluate log base 3 of 9. By the way, log base 3 represents a function, so more and more I like to put parentheses around the argument, the 9 here. All right, so some people call this the box method, where we set this equal to a box, which will contain our answer. And we're asking 3 to what exponent is going to give us 9. 3 to what exponent gives us 9, right? Let's go over here. Three to what exponent, the box, is going to give us 9? Well, 3 to the second gives us 9, and that's going to be our answer, our logarithm. Okay, so 2 is our answer. Log base 3 of 9 equals 2. That's the logarithmic form. When we did the zigzag, that was the exponential form. 3 to the second is 9. So mentally, I like to lower the 3, raise the 9, and I'm asking myself, 3 to what exponent is 9? The answer is the 2 here. Okay, let's do some more examples. We're going to think zigzag. Okay, got to be careful here. Okay, so log base 5 of 1/5 is what? So we can imagine a box over here. All right, 5 to what exponent is 1/5? Well, 5 to the negative 1 is 1/5. Erase all this. 5 to the negative 1 is 1/5. Negative 1 is our logarithm. Next, let's look at this over here. Log base 9 of 3 is what? 9 to the what is 3. And this is going to be a little bit trickier. 9 to the what is 3. Well, how's 3 related to 9? 3 is the square root of 9. What's the square root of 9? It's 9 to the 1/2. 9 to the 1/2. So 1/2 is going to be our logarithm. Nine to the 1/2 is 3. The square root of 9 is 3. This bottom one is a trick question. 10 to the what is 10 to the 7th? 10 to the 1 is 10 to the 7th? Let's take a look at that. 10 to the what is 10 to the 7th. This is all a mess. Let me erase this. All right. 10 to the what is 10 to the 7th. Well, 10 to the 7th is 10 to the 7th. A horse is a horse. So the answer here is going to be 7 because a horse is a horse. 10 to the 7th is 10 to the 7th. This is a demonstration of an inverse property because log base 10 and the base 10 exponentiation function are inverse functions. They undo each other. So the 7 here becomes the 7 over there. We've seen this before with things like cube root and cubing. Okay, so in our next video, we're going to talk about logs with particular bases, some special types of logarithms. So until next time.
Any questions so far? Because some people have difficulty with these fundamentals of logs. That's what turns them off. Any questions? Any questions before we go on? Okay, reviewing logs. Okay, and thank you for participating in the chat. Yes. All right.
Hi, everyone. Let's continue with section 3.2 on log functions. All right, so there are different types of logarithms with different bases. So over here, common logs. These have log base 10. F of x equals log base 10 of x. Again, I like to put parentheses here. This gives the common log function. Now, instead of log base 10, we usually just write log of x. And on your calculator, you should see an log button, which gives us common log. In other cases, when I say log, I might mean a generic logarithm. Here, we mean a common log. So if you don't see a base in a particular problem, assume it's 10. Now, common logs are used in the Richter scale for measuring earthquakes, although there are more sophisticated scales nowadays. Also, they're used in the pH scale for measuring acidity in chemistry. So, for example, something that's a pH of 4 is going to be 10 times as acidic as something that's a pH of 5. Back to the Richter scale, bear in mind that an earthquake measuring a 7 on the Richter scale is 10 times as powerful as one measuring a 6.
Now I need to point out, because I have a colleague who's a geologist. He's in New Zealand right now. Good country to be in right now. The magnitude of a 6 earthquake is 10 times as powerful, 10 times as powerful in magnitude. But a 6 earthquake releases 31 times as much energy, though. Okay, 31 times as much energy. So keep that in mind.
Now that's in terms of magnitude. Actually, in terms of energy, a 7 earthquake releases 31 times as much energy as a 6 earthquake. So a 7 is much more devastating than a 6. Now, if you want to compare a 7 versus a 5, by magnitude, a 7 is 100 times as powerful as a 5 in terms of magnitude, but it's 1,000 times as powerful in terms of energy released. By the way, negative Richter numbers are also possible, very weak earthquakes. So common logs are base 10. Natural logs are base E. E is our favorite base, remember. Okay, so if f of x equals log base E of x, that gives the natural log function. Instead of log base E, though, we always write ln. Not ln or ln, ln. So in a final answer, if your final answer is log base E of 7, you'd write ln of 7. Although the log base E form can help us in our work. Now, just as log is common log on your calculator, ln is natural log on your calculator, E is the implied base. By the way, never write ln base E. That's redundant. Do one or the other. It's either log base E or just ln. Really, you should just use ln in a final answer. One reason why we like this type of logarithm is that the derivative of ln of x is 1 over x. That's not quite true for other logs, like log base 2 of x. Okay, so let's do an example. ln of e to the 5th. Again, I like the parens here. ln of e to the 5th. As part of your work, you might want to write ln as log base e. So what's log base e of e to the 5th? Well, e to the what is e to the 5th. E to the 5 is e to the 5th. Again, this is a demonstration of an inverse property. These guys undo each other. The final answer is 5. Okay, see you in the next video.
And I mentioned common logs earlier.
Hi, everyone. We're continuing with section 3.2 on log functions and their graphs. So before, we talked about common logs, log base 10 of x, and natural logs, log base e of x. But let's talk about logs in general. What are some properties that logs of various types have in general? What are the properties of logs? All right, so I'll need to be careful here. We're going to play peekaboo. All right, let's talk about properties of logs. All right, basic log properties. Now we're going to assume that b is any nice base. Remember, a nice base is a positive number that's not 1. So we actually get an exponential function and a corresponding logarithmic function. All right. So first property, log base b of 1. And again, I tend to like to put grouping symbols around the 1. All right, b to the what is 1. B to the 0 is 1. That's true for any nice base b. All right, so this is the log form. Here's the corresponding zigzag, the exponential form. B to the 0 is 1. Now, we're especially curious about what happens when the base b is our favorite base, e. Well, if log base b of 1 is 0 in general, then in particular, log base e of 1 is 0. And remember, instead of log base e, we write ln. So it's good to know that ln of 1 is 0. That's a good thing to memorize. So this last column here is a column that you should memorize. And then just remember that these statements here will extend to other nice bases, not just e. All right, next one. For any nice base b, what is log base b of b? B to the what is b? Well, a horse is a horse. B to the first is b to the first, right? So the log here is 1. 1 is the exponent that takes you from b to itself. In particular, log base e of e is 1. In other words, ln of e is 1. That's what you really memorize. How about log base b of b to the x? B to the what is b to the x. Again, it's another horse is a horse problem. B to the x is b to the x. This is like a special case of this where x is 1. Okay, so in the special case where the base is e, log base e of e to the x is x. Or, in other words, ln of e to the x is x. And this is an example of an inverse property where these two functions undo each other. They're inverses. So the x here becomes the x here. The composition of these guys is the identity. Now, there's another inverse property that we need to look at. It's this over here. B to the log base b of x. So here, we're logging first and then doing the exponential function. And once again, the answer is going to be x. But we do have a condition here. It turns out that we only take logs of positive numbers. We'll talk about this. So this property only works if x is positive. We only take logs of positive values. We'll discuss that. All right. What's a way of seeing that? Okay, well, log base b of x, that's the exponent that takes us from b to x, right? So think of the box method, right? B to the what is x. So instead of this, imagine the box, right? Well, b to the what is x. You're going to get the same number up there. So imagine replacing this with the box, and you're basically saying the same thing over and over again. In the special case where the base is e to the log base e of x is x, or e to the ln of x is x. Again, these two functions undo each other. Okay, so I'll take up the markup tool here. All right. Remember, we like to put parentheses normally around the arguments. Ln of 1 is 0. Ln of e is 1. Ln of e to the x is x. And e to the ln of x is x. You should memorize these four. Ln of 1 is 0. Ln of e is 1. Ln of e to the x is x. Also, e to the ln of x is x, provided that x is positive. And you extend these to logarithms in general, where the base is any nice base, not just e. So these work if the base b is 2, 3, 4, 10, and of course e, and so forth. Now, I'd like to discuss this restriction a bit more. Why do we only take logs of positive values? All right, the log of a non-positive number is not real. That's the problem. It's a problem of keeping it real. So in this class, we only take logs of positive real numbers. Now, I know we've dealt with I before, but we're never going to mix imaginary numbers and logs. You do that later in a complex variables class, which electrical engineers do take. All right, example, log base 2 of 1 is not real. Try the box method. Log base 2 of negative 1 is what? Can we get a real number to fill in that box? Well, does 2 to a real number equal negative 1? Look at this. Does 2 to a real number equal negative 1? No. Nobody does that. Nobody does that. So this thing here has no real solution for the box. So what we say is that log base 2 of negative 1 is either undefined or not real. Actually, you could say that an imaginary number could correspond to this, but we're going to keep it real. And this thing is not real. Also, observe that it's a range issue here. Observe that negative 1 is not in the range of the 2 to the x function, right? Only positive numbers are in the range of the 2 to the x function, so this thing has no real solution. That's what I mentioned over here. Similarly, how about log base 2 of 0? Well, again, that's not real because 2 to the what is 0. 2 to the what is 0. Well, I can't fill in that box, not even with an imaginary number. So log base 2 of 0 is not real. In fact, more so than before, it's undefined. Log base 2 of 0 is just a mess. So we can take log base 2 of any positive number, but we do not take log base 2 of a negative number or 0. And that's true for all logarithms. Okay, once again, the last two properties are called inverse properties. These functions undo each other. The x's here become the x's there. All right, so next, let's discuss these inverse properties in more detail, all right? So let f of x be b to the x, where b is a nice base, like e. And f inverse of x, it turns out to be the corresponding logarithm, log base b of x. So these two guys are inverses of each other. They undo each other. And we saw that in those two rules up here, right? They undo each other, just like the cube root of x cubed was plain old x. They undo each other. All right. So what do we know about inverse functions? Remember that the graph of y equals e to the x was that J curve, right? Because the base here was greater than 1, And the graph of y equals e to the x is going to give us this j curve. Now, if we're going to graph the inverse function, what do we do? Remember, the line of reflection is given by y equals x. It was this over here, remember? Y equals x. When you invert this guy over, this was a homework problem, you get this. Here's a nicer picture. All right, so here's the graph of y equals e to the x. It's the j curve, right? Y equals x, the dashed line here, not an asymptote, but it's a line of reflection. When we reflect the red graph, we get the blue graph over here. This is the graph of y equals ln of x. It's kind of like a square root concave down hook, except it does not start at the origin, and there's actually a VA there. Speaking of which, notice that the red graph, y equals e to the x, has an HA, a horizontal asymptote, while the graph of y equals ln of x, the blue graph, has a VA, a vertical asymptote. What else do we notice? Well, remember, if the point AB lies on the original graph, the point BA lies on the new inverse graph. So if the point 0, 1 is a y-intercept on the red graph here, then the point 1, 0 is an x-intercept on the blue graph here. AB goes to BA. So the intercepts basically switch over. Okay, now what else will switch over? Remember that for a pair of inverse functions, we're switching inputs and outputs, the set of inputs and the set of outputs, which means that the domain of one becomes the range of the other, and vice versa. All right, so let's remind ourselves. For the e to the x function, right? For the e to the x function, what was the domain for this? Well, think x coordinates. We pick up every real number as an x coordinate on this j graph. So the domain for the e to the x function is all real numbers. What about the range? Well, the range is y. It's only the positive reals. We only pick up the positive real numbers as the y coordinates. So once again, the domain for the e to the x function is r, all real numbers. The range is the positive reals, the open interval from 0 off to infinity. And again, the x-axis is a horizontal axis. Now, when we consider the inverse function, y equals ln of x, remember, the domain here is the range here, the range here is the domain here. The domain for the natural log function is the positive reals. Notice the only x coordinates we pick up on the graph are the positive reals. The range is the set of all reals. All real numbers work as y coordinates. These y coordinates do go off towards infinity, kind of like square root. There's no HA for this guy. However, there is a VA for the blue graph. So the HA for the red graph, the original function, becomes a VA for the blue graph, the new inverse function. Remember, the domain of one becomes the range of the other, and HAs and VAs basically switch here. All right, next up, let's talk transformations. Hey, these are functions, so we have the same old rules. All right, let's consider f of x or y equals ln of x minus 3, this transformed log guy. All right, let's write the domain of this in interval form. Remember, this is real if and only if the argument here, x minus 3, is positive. We only take logs of positive values, but we can take the log of any positive value. So to find the domain for this whole thing is real if and only if the argument x minus 3 is strictly positive. It cannot be 0. Add 3 to both sides, x is greater than 3. So the domain in interval form looks like this, the set of all real numbers that are greater than 3. That's an open parens, not a bracket. And that makes sense because let's take a look at Desmos. All right, so here's the graph of y equals ln of x, that hook, right? Notice the y-axis is a VA, x equals 0 is the equation. Let's graph y equals ln of x minus 3. When we substitute x with x minus 3, remember we translate the red graph to the right by 3 units over to the green graph. By the way, this is a horizontal translation. It may not look like it because I think our eyes are tempted to look for perpendiculars here, but this is a horizontal translation of the original. Think horizontally, 3 units, 3 units, 3 units, 3 units. I know our eyes have a hard time seeing that, but we do have a 3-unit gap horizontally between the two graphs. So what's the domain for this transformed function? Well, the new VA, by the way, is at x equals 3. The purple line is the new VA for the green graph. What are the x coordinates we pick up on the green graph? All real numbers strictly greater than 3. All real numbers strictly greater than 3. The range, again, is all reals. All right, so the domain, we've confirmed it, all right? And here's another version of this picture over here. Remember, we like to put dashed lines as asymptotes. Red graph, VA here, 3 units to the right. The blue graph, VA here. The domain is also shifted by 3 units. All right, so that is section 3.2. I'll see you next time.
All right. So are there any questions before we go on? Any questions before we go on? Let's see. Question. Can I discover the range without the graph? Oh, good question. The graph helps a lot. Gosh. Well, if you know that it's just a horizontal translation. I mean, the thing is, you may not be required to show work in that sense. You just have a sense of logs, right? But you know what? I think a graph is just very helpful, right? Because we associate range with y coordinates. It's just kind of hard to think about range, right? The possible outputs. I think a graph helps a whole lot. So I guess in principle, sometimes you figure out the range, like x squared, right? You know, the range of x squared is the non-negative reals, right? But sometimes a graph is very helpful. Yeah.
Is in front, okay? Unless you have like a negative exponent on here, all right? So it's minus log of
Okay.
t.
Oh yeah. Well,
People.
all right. There we go.
Hi everyone. This is section 3.3 on more properties of logs. And a lot of people get confused by these, but they're beautiful and awesome once you master them. Now, first of all, let's learn how to read log expressions, because in my notes and in old books, it can be kind of ambiguous what something really means. So, for example, remember that if you want to talk about ln of x, right, I strongly recommend that you put parentheses around the argument. Okay, in my old notes, I was kind of sloppy about that, and many books are sloppy with that. So if you're kind of confused what an expression really means, let's look at some conventions. And you see this on the homework as well. So we will use grouping symbols, ideally, as a means of clarifying the order of operations in expressions. Often grouping symbols are omitted when they could have helped. How do we read log expressions in these cases? Now here, I'm going to use ln, the natural log for convenience, but these are issues with various log functions, common log, log base 4, whatever. All right, so for example, if you see something like this in a book, all right, ln 3x plus 7. Normally, the ln is considered to apply to products, powers, and quotients that follow it. So over here, it's assumed that the argument is 3x. We're taking the natural log of 3x. If you want to do overkill, you could put all this in brackets, okay? And then the 7 is added to the whole thing over here. But if you see ln 3x plus 7, the ln is assumed to apply to the 3x. 3x is the assumed argument, and the plus 7 is loose. It's out there. If you actually want ln of the quantity 3x plus 7, put parentheses around the whole thing in here, 3x plus 7. Okay, ln 3x to the fourth. Again, for products, quotients, and powers, we assume that the ln applies to this mix over here, and all of this is the argument. bear in mind, if you use Wolfram alpha, sometimes there's some ambiguity even for something like this, ln of x to the fourth. Ln of x to the fourth. Okay? Now, normally the way the books would interpret this, most books would interpret this as ln of the argument x to the fourth. But Wolfram alpha has this legitimate idea that functions bind more tightly than exponents. So Wolfram alpha is more inclined to say that this is ln of x all to the fourth, which is really stressing as to why it is that you really should put parentheses around your arguments so there's absolutely no confusion, and put parentheses around complicated bases as well. Basically, use grouping symbols. They can help a lot. All right, ln x to the fourth, as I just said, most books would interpret that as x to the fourth being the argument, but Wolfram alpha may interpret it like that. But these are not the same thing. These are not equivalent. So it's important that you know how to read this. So as a student, you should write this as either this or this to be super, super clear. In fact, you might even want to do overkill and put the parens around the x. All right. Again, generally speaking, if these guys are followed by a product quotient or power or a mixture of those, then the log is assumed to apply to the whole expression that follows. If you have plus or minus signs, they tend to break things off unless things are in grouping symbols. All right, so enough for reading. Log properties based on laws of exponents. All right, so remember that logs are exponents, and the laws of exponents directly translate to laws for logarithms. Okay, now remember, we only take logs of positive values, okay? So we're going to assume here that A and B are positive, where A and B represent maybe constants or variable expressions. Back here, we're going to state these properties using natural log, ln, but again, these apply to any log function with a nice base. And we have to be consistent. If we're talking about log base 4, for example, I'm assuming we're talking about a bunch of log base 4s. We don't want to mix log base 4 and log base 5, say, just yet. We'll need the change of base property later on. Okay, in one direction, from left to right, we're said to be expanding the expression. From right to left, we're going to be condensing the expression. Okay, so what's an example of a log property? Well, let's go back to a basic law of exponents. X to the second times x to the third. How do you simplify that? Well, this is going to be x to the fifth. Why? You did that automatically. What did you do? Well, when you multiply powers of x, you add the exponents. 2 plus 3 is 5. So the exponent on a product is the sum of the exponents, all right? Exponents are logs, right? So what are we saying here? What are we saying here? I'm going to move this down. Well, okay, let's not then. All right. The product rule. ln of AB equals ln of A plus ln of B. The logarithm on a product equals the sum of the logarithms. All right, so I'm going to rewrite what I wrote above. X to the second times x to the third is x to the fifth. All right, so in order to find the logarithm, the exponent for a product, what do? You take the sum of the exponents of these guys over here. The exponent or logarithm on a product is obtained by the sum of the exponents. The log of a product is the sum of the logs. The log of a product equals the sum of the logs. Here I use powers of e. Okay, likewise, we have a quotient rule. Right? So remember, x to the fifth divided by x to the third is going to be x to the second, right? What did you do? When you divide powers of x, you subtract the exponents. The logarithm on a quotient, the 2 here, is obtained by subtracting the exponents or logs over here, all right? 2 is 5 minus 3. The log of a quotient equals the difference of the logs. When you divide powers of x, you subtract the exponents. That's the idea. Here's a related idea with powers of e. Okay, so if you agree with these basic rules for products and quotients for exponents, then you should agree with these rules for products and quotients involving logarithms. All right, by the way, don't confuse this with ln of a over ln of b. That's different. That's the change of base property. A lot of students confuse those. Again, grouping symbols, critical. Now for our next property and our next rule, the power rule. All right, so let's say we have x to the second all raised to the third. That's x to the what? It's x to the sixth, x to the sixth. Because when you raise a power to a power or exponent, you multiply the exponents. The power rule. All right, so when you take a log of a power, okay, a to the p, I should put grouping symbols here, you can smack down the p. That's like WWE smackdown. You can smack down the p. The basic idea is that in our example here, x to the second itself was a power, right? And we're raising a power to an exponent. So we have this power guy being raised to an exponent. Okay, the exponent comes down. ln of a was the exponent. It was the 2 up here, right? Basically. So 6 is 2 times 3. Okay, 6 is 2 times the 3. Okay, that's basically being smacked down. That's the idea. All right, the smackdown rule. So again, from left to right, it's expansion. From right to left, it's condensation. Okay, from left to right here, that's the smackdown rule. We can smack down the p. That's expansion because this is kind of an expanded, longer expression, bigger expression. I call the reverse the basketball rule, going from right to left. You can throw up the p like a basketball and get that. That's condensation. This is a shorter, more compact expression. Going backwards, the product rule, going from here to here, that's expansion. You're making it longer. Going from here to here, that's condensation. You're making it more compact. For the quotient rule, going from here to here, that's expansion. You're making it longer. From here back to here, that's a condensation. You're making it more compact. All right. Now,
By the way, before I go on,
this is key. Just like we don't have a rule for the square root of a plus b, remember we do not have a rule for something like this, right? You may just leave it be. Likewise, we don't have a rule for the log of a sum or a difference. So basically, don't break this thing up. As it stands, you cannot break this thing up, all right? So if you see something like ln of a plus b, you typically leave it. Okay, I would like to go back to the power rule because, well, as they said in Spider-Man, with great power comes great responsibility. Okay. Now, before we get to the power rule, one quick idea here. If you forget the rules, you might be able to use powers of e. So for example, to test out the product rule, you can plug in a equals e to the second, b equals e to the third, work it all out, and you'll get 5 equals 5. See, if you had made the incorrect assumption that the log of a product equaled the product of the logs, then you would have gotten 5 equals 6, and you knew that you were on the wrong track. By the way, that's a good way of looking at these rules before we get to this abuse of power that I'm going to talk about. Going back to the product rule, I often think of it this way. The log of a product is not the product of the logs. It's not ln of a times ln of b. It's the sum of the logs. You're going one step down in the order of operations. The quotient rule. The log of a quotient is not the quotient of logs.
by the way, I need to explain that. I don't like PEMDAS. I like PIMA because remember, multiplication and division are tied. Addition and subtraction are tied. So when I say one step down, I say going the step down from multiplication and division down to addition and subtraction. That's what I mean. Because PEMDAS ignores ties.
ln of A over ln of B. Instead, it's the difference of logs. The log of a quotient equals the difference of the logs. Okay, power rule, once again, is the smackdown rule. Okay. You can smack this guy down. Now, the power rule, again, we're in danger of abusing, and with great power comes great responsibility. The Spider-Man quote. Okay, so how not to abuse power? Let's not be a politician. How not to abuse power. But like a politician, I'm going to cover up. All right, more on the power rule. So basically, what can you do and what can't you do? What can you do and what can't you do? That's an important theme for this class. All right, so once again, the power rule for logs is the most commonly abused rule of these three. All right, so in the following examples, yes or no, are the two expressions equivalent, assuming x and y are positive, or are they not equivalent? Could we find counterexamples? Over here, ln of xy to the third. First of all, let's read it. ln of the argument xy to the third. All right, now, can we smack down the 3? Can the 3 come down? The answer is no, because the x is in the way. You have to ask yourself, what is the base for the exponent? Is it xy? No, the base is only the y here. So no, if a student tries to smack down the 3, that's wrong. These are not equivalent. The 3 does not apply to the x, it only applies to the y. So in fact, you'd use the product rule first. You'd want to break this up using the product rule. The log of a product equals the sum of the logs. We'll talk about that later. Okay, our next victim here, ln of the cube of xy. We're assuming the ln applies to the whole power here. Can we smack down the 3 in this case? And the answer here is yes. The 3 can come down 3 times ln of xy. By the way, I just realized it might be a good idea to even put brackets around this guy over here. The 3 can come down 3 times ln of xy. We would have equivalence here, and I would put parentheses around the xy, because the 3 applies to the entire base here, xy, all right? So the 3 can come down, xy, the argument here, okay, was the base over here, so that works out. Again, I'm assuming x and y are positive in value. Next, the cube of ln of x. Here, grouping symbols aren't so necessary. This is fairly clear. The cube of ln of x. Can we smack down that 3? Can we do this? And the answer is no, we cannot do that. Because if the natural log is part of the base, we simply cannot do that. There's no rule for that, okay? Because since the 3 applies to the ln as well, we're not allowed to smack down. So when are we allowed to smack down? Okay, in this case here, ln of x cubed, I'll go ahead and mark it up here, ln of x cubed, okay? Here, 3 only applies to x, not to ln, so the 3 does in fact smack down. ln of x cubed is 3 ln of x. These are equivalent. So the power rule, don't abuse it. Know when you can use it and know when you cannot. Over here, the 3 does not apply to the x. We cannot smack down the 3. Over here, the 3 applies to the xy. Again, it might be a good idea to put brackets around this to make that clearer, that we have ln of all this. The 3 we can smack down. Over here, the 3 applies to this whole log guy. We're not allowed to smack down the 3. Here, the 3 only applies to the x. We can't smack him down. All right. So do not abuse power. One side note, and this will bite you once in a blue moon. Let's say we have ln of a squared, all right? But what if we allow a to be negative in value, all right? Well, then when we smack down, technically, we're supposed to put absolute value. So if you're smacking down an even exponent, like a 4 or a 6 or an 8, and a could be negative, then you should put absolute value. That's kind of similar to the idea that the square root of x squared, remember, was not in general just x. It was the absolute value of x. And this is a similar idea. It may bite you once in a while. Okay, so now let's apply these rules in actual expressions. All right, homework problems. Expanding log expressions. So first of all, let's expand this over here. I'll blow this up a bit. Let's expand ln of the cube of ex. Sorry, the cube root of ex. Okay, now first of all, notice that we're taking the natural log of all of this, and overall, we're taking the log of a power. How can you rewrite this as a power? This is ex to what exponent? This is ex to what exponent? When you take a cube root, you're raising something to the 1/3 exponent. Okay, here it is much nicer. Again, you may want to put brackets to be super clear. All right, so ln of the cube root of ex, okay, that's ln of ex, that's to the 1/3. Now, what can we do with the 1/3? Yes, we can smack it down. 1/3 ln of ex. And remember, I'm assuming here that all variables are restricted to positive values. Okay, so the 1/3 smacks down. We now have this. But we're not done, because I can expand that. The product rule. The log of a product equals not the product of logs. It's the sum of logs. So 1/3 times, and a lot of people forget these grouping symbols. You really need these, because the 1/3 applies to all of this. Common error, by the way, to forget these. It's 1/3 times all of this. The sum. The log of a product is the sum of the logs. ln of e plus ln of x. The parentheses aren't so necessary over here for the e or the x. But wait a minute. You must evaluate ln of e. You can simplify that. What is ln of e? It's 1. You better remember that. So when you're expanding this over here, we get this. Now, some people might say, well, shouldn't we distribute the 1/3? You could, but I wouldn't require that. If you write this, I'll call that expanded, although you could distribute and get this over here. All right. So we've expanded. We've turned this compact expression and made it longer. So why would we want to do this? In calculus, if you're asked to take the derivative of this, you'd much rather rewrite this as this, and derivatives are much easier to take when you have something of this form. Derivatives tend not to like powers or roots as much. So log properties are your friend. Calculus would rather have you write this as this. It's easier to take derivatives and also integrals. Okay, next example. Let's expand log base 2 of the fraction, this quotient, 8x cubed over y. We're taking the log of a quotient. Now, the log of a quotient is not the quotient of logs, it's the difference of logs. And remember, it's log base 2. Be consistent. All right, so log base 2 of this equals log base 2 of the top, 8x cubed, minus log base 2 of the bottom, y. Now, actually, you can skip this step if you go all the way and apply the product rule over here. Basically, you can skip maybe a step or two as you do these problems, because there is a pattern that we'll see. In fact, for some problems, I might accept answer only, because by the time you take calculus, you get so good at ripping this apart and evaluating little pieces. But for now, let's do it step by step. Okay, here we're taking the log of a product. The log of a product is not the product of logs, but the sum of logs. Log base 2 of 8 plus log base 2 of x cubed, and then minus log base 2 of y. Don't forget the little 2's here. It's a mistake to forget or omit those little 2's. You must put them all in. Now, many students will be able to go straight from here to here directly, right? Factors of the numerator, they're going to correspond to plus signs in front. Factors of the denominator, they're going to correspond to minus signs in front. So with time, you'll be able to go from here to here pretty quickly. But there's still more to do. Over here, what is log base 2 of 8? 2 to the what is 8? 2 to the what is 8? Well, 2 to the third is 8. Also, what can we do with this 3? Well, the 3 is on the x. We can smack the 3 down by the power rule. So we get 3 plus 3 log base 2, don't forget that, of x minus log base 2 of y. And that's that. Don't try to tear these apart. Okay. Next. This, I would accept answer only. It helps that we assume it's a common log. We don't have to keep writing 10. But it turns out that we can write this in one step in calculus. All right, so what's the bottom line? Factors of the numerator are going to have plus signs in front, unless maybe you have negative exponents. Factors of the denominator are going to have minus signs in front. All right. Step by step, the log of a quotient, right, is not the quotient of logs, it's the difference of logs. Okay, basically, I could have started like this. The log, maybe I should have put this step at first. Log of a squared b cubed, all right, minus, I'm applying the quotient rule, log of c to the fourth d. Okay, so if you want to apply the quotient rule directly, you get that. Log of the top minus log of the bottom. But here, we're taking the log of a product. Here, whoops, here, log of a product. Use the product rule. The log of a product is the sum of logs. The log of a product is the sum of logs. And once again, we need these grouping symbols, those parentheses. So then, when we expand this thing out, all these exponents then smack down, all right? We get, and again, many students can go from here to here, we get 2 log of A plus 3 log of B minus 4 log of C minus log of D. Now, I must stress this. This is by far the most common error that students make on an exam. They don't know that's a minus sign because they fail to group over here. Remember what I said earlier. Factors of the denominator ultimately are going to lead to minus signs in front, okay? Unless you have like a negative exponent on here, all right? So it's minus log of D. The D here is a factor of the bottom. One way to see that, be careful with grouping symbols up here. But again, in calculus, you should be able to go from here to here in one step. 2 log of A plus 3 log of B minus 4 log of C minus log of D. All right, now why would we want to tear this thing up like that? Well, like I said in calculus, instead of taking the derivative of that, we may rather take the derivative of that. Okay. Now how about a condensation problem? Let's do a couple of these.
Okay. Before I go on, are there any questions? Okay, applying the product quotient and power rules, and keep those grouping symbols in mind, or know the shortcuts very well. Any questions? Any questions? We're in the last phase here, okay? Oh, we have about 3 minutes left. We're almost done.
Let's condense ln of x plus 3 ln of y, all right? Now, this 3 is really in the way, right? He's in our way. So what can we do with this? Well, basketball, the power rule in reverse, all right? The 3 goes up here. So then we have ln of x plus ln of y to the third. Again, let's assume that x and y are positive in value. Now what do we have? I'll put parens here. The sum of logs. The sum of logs was the log of the what? It wasn't the log of the sum. It was the log of the product. So we have ln of xy cubed, and that's that. Actually, we talked about him before. He was way up here, remember? Okay, ln of xy cubed. We talked about him way up here. Okay. All right. Let's condense this. All right. So 1/2 log of 3x plus log of y minus 3 log of z. Once again, these coefficients sort of are in the way. So what do? We're going to play basketball. Move up the 1/2, move up the 3. And I'd recommend moving up a 3, not a -3, because then that'll be confusing. All right. So we bring up the 1/2 over here. And remember, we need grouping symbols because the 1/2 applies to all of 3x. For good measure, I'll put brackets here. And parens over here. Okay, so log of the 1/2 power of 3x, which is the square root of 3x, plus log of y minus log of z to the third, the power rule. We're condensing. All right, bottom line. The sum of logs is not the log of the sum, it's the log of a product. And then the difference of logs is not the log of a difference, it's a log of a quotient. Again, sum of logs, log of a product, difference of logs, log of a quotient. But with time, you should be able to go maybe from here all the way to here even, okay? Or at least from here to here. All right, so log of, I'll put the y in front, because remember, you're not supposed to extend that radical too far. Y times the square root of 3x all over z cubed. Now, why would we want to do this? Well, this comes up if we're solving equations. Let's say we want to set this equal to 0 and solve that equation. It turns out to be better to condense this like so and figure out where this thing is equal to 0. Okay, so that's all for now. In the next lesson, I'll discuss the final part here, the change of base formula. But we'll wait till next time.
By the way, at this point, you can do all the homework. If you're following the videos and lectures, you can do all the homework through 3.3, number 4. So basically, all but number 5. All right. But if you're brave, look ahead, you know. But, okay, we're done through most of 3.3. I could do 3. I could do the very last part, but I think we're all kind of overloaded. So let's go ahead and now. I do want to note here. I didn't make this, but this is a nice little guide going from the laws of exponents to the laws of logs. I may email this out at some point, right? Okay, but I think we've had a good solid day. All right. Okay, I have 9:25. I'll take questions at this point. We're done through almost all 3.3. All right. Any questions? Any questions? Okay, I'll keep this recording unless anyone objects.
Professor, I have a question.
Okay, go ahead.
On section 2.6, 1A, I don't understand why is there no holes?
Okay, so we're, let's see here.
2.6.
Yeah. Okay, so let's see, homework. Okay, let's see. I'll grab a new copy then, all right? Let's see, math. 2, okay. All right. All right, good. Okay. Oh, sorry. Which one again?
2.6, 1A.
2.61A.
Because what I solved the denominator, and so it wouldn't be equal to 0, and I had -1 and 3/2 as zeros of my denominator, and I thought they were gonna be the holes of the.
Okay, now the thing is, this is simplified. They're going to be VAs. They're going to be VAs. Remember, if you have an expression that's simplified, this is simplified as it turns out, though you don't know that till you factor it, then the real zeros of the denominator will give you VAs. Actually, there are no holes.
Oh, okay. So, okay, I see. So instead of holes, they're the VAs.
Right. Okay. So because it's simplified. Okay. So
Okay.
remember, if simplified, if the thing's already simplified, okay, then the real zeros of the denominator will correspond to VAs. Okay. Now, if it's not simplified, you could get holes, okay, or VAs at the real zeros. And that depends on whether the corresponding factors are eliminated in the bottom or not. If they're eliminated, you get holes. If they're not, you get VAs.
Okay.
Yeah.
Cool.
So that's one way of looking at it. When you factor the bottom, those factors still survive, right? There's no cancellation. They don't get canceled out. So these factors still survive. You have VAs at the corresponding real zeros.
Mm-hmm.
Yeah.
And then if you cancel, you get holes.
Right. If you get a complete cancellation, right? If you have, let's say, for example, you have an X up here and X, and an X down here, let's say, okay? And let's say that X, these are all the X factors on top. Okay, right? We factor the GCF. We have all the X factors on the bottom. Okay, we factor the GCF. Bye-bye. You get ones, but you get a hole at X equals 0.
Mm-hmm.
Because that guy's canceled. And the same thing happens if this were a square, a cube. Basically, the guy down here dies. That X factor down there dies. Yeah.
Got it. Thank you.
You're welcome. Yes, yes. But yes, that whole issue, holes versus VAs, yeah, that's tough for people, even in calculus. But it's good to get a taste of this, a preview in your pre-calc class. All right. Okay, I will take any other questions. I'm still recording. If you object, let me know. But I think students really appreciate having the recording. Okay, and thank you all, by the way. Thank you all. Have a good night. I'll see you Thursday, most of you. I'll stick around for questions. Or if you'd like me to wait for like 5 minutes, I can do that too. Okay, any questions? Any questions? Okay, so I see some requests here. 2.5. Okay, 2.5, 2H. Use synthetic division to show that. Oh, okay. Well, first of all, it's good to have at least C done first. Yeah, from task C, right? So I'm going to do it from C to G to H. All right. And I wonder, I may have done this earlier, but I'll go ahead and do it again. So when you do the synthetic division, okay, 3 is in the dunk tank, right? And descending powers, no missing terms. 2, -3, -17, 12, and 36. So I got to go back here. Blank space, bring down the 2, multiply by 3, add, multiply by 3, add, multiply by 3, add, multiply by 3, lo and behold, add. If I made this bigger, I'd put a smiley face here. A little smiley face. All right. We're good. We like this. Is 3 a 0 of G? Yes, it is, because that's a 0 down there. Remainder theorem. G of 3 is 0. All right. So these will help us construct the other factor. So from task G, we know that we have T minus 3. And what's C of T? What's the other factor? The coefficients are given by this guy. So what's this C of T thing? It's going to be 2T to the what? We have a 4th degree divided by a 1st degree as a 3rd degree. 2T cubed plus, 3T squared minus 8T minus 12. All right. Now, see, before in part D, I asked you to do factoring by grouping, okay? But a lot of people wouldn't notice that, right? A lot of people aren't too familiar with factoring by grouping. So actually, a lot of calculus students might actually resort to the rational zero test, and we're hoping that not just 3 will work, but maybe something like -3/2, okay? And we apply it to this guy, the quotient, the third degree quotient. -3/2 over here, right? And then you repeat this row over here. 2, 3, -8, -12, all right? So why don't I stop here? Try to proceed from there, okay? And that should be the key hint. So go ahead and proceed with this synthetic division from here. And then, we can talk about this later on, next time maybe, if you have trouble, all right? So let's put this in the bank for now, all right? Let's go to 13b. All right. List the possible rational zeros, all right? Factors of this over factors of 1, all right? Well, it's going to be plus or minus. Well, since we have a 1 here, we don't even need fractions. It's going to be plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. Those are the possible rational zeros. Okay, by looking at this, see, the thing is, -21 is pretty powerful, so I don't think 1 or -1 will work. Will 3 work? Let me try 3. All right, coefficients are 1, -1, 1, -21, 1, -1, 1, -21. Bring down the 1, multiply by 3, add, multiply by 3, add, multiply by 3, add. We're happy with the 0 there. That's a 7, by the way. All right. So how do we factor this over the reals? Because 3 is a 0, what has to be a factor? I'll do this in red. Because 3 is a 0, what has to be a factor? It's x, right? X minus 3. All right. If you divide a third degree by a first degree, you get a second degree. X squared plus 2x plus 7. And if you use the test for factorability, you'll see that the discriminant, b squared minus 4ac, is not a nice square. That's factored over the reals. I believe that's the correct answer. Let me check. Where are my answers? Yeah, I think this one here, right? Yeah, okay. Right, x minus 3 times the factor x squared plus 2x plus 7, right? And then for C, to find the complex zeros, you QF this thing. So use the quadratic formula on that. And also 3 will be a complex zero. Okay, so, right. All right. Any questions? Oh, I'll wait another minute. Oh, good, good. Oh, welcome. Any questions? If not, at 9:38, I'll pause and I'll take a 5-minute break. Okay, you can gather your thoughts, and then at 9:43. Oh, okay. Let me look at this. Okay, 25 number 8, 25H. Yeah. Wait, what? 2H. Okay. So I started this. Would you like me to continue with this one? Is that right? All right. So again, we're doing synthetic division with the new quotient, right? With the quotient here, that's the new dividend. Bring down the 2, multiply, that's a -3. Add, multiply, add, multiply, good, 12. Add, 0, perfect. All right. So -3/2 is a 0 for this over here, because when you plug in -3, you get 0. That's by the remainder theorem. All right. If you call this thing C of t, C of -3/2 is 0. C of -3/2 is 0, where this is C of t over here. It's the other factor. Okay. So the original factors as t minus 3 times this guy over here. All right. So now what do we have to factor completely over the integers? So remember we had the t minus 3 over here. Times the C of t guy. All right. But what happened? -3/2 is a 0 of C. So that means that T, what, is also a factor. T plus 3/2 is also a factor. Okay, and now you have, from here, 2t squared minus 8. All right. Hint, factor out a 2. Okay, you can factor out a 2 from there. So those are some key hints. And also, when you do that, you find that you're going to get t squared minus 4. You can also factor that. So, okay. So we're talking about factoring over the integers. Oh, okay. So there are a couple things we have to do here, actually. So equals, you have the 2 in front, t minus 3 t plus 3/2 factor out of 2, t squared minus 4. All right, 2 things. So here are 2 key hints. 2 key hints. Okay, we want to factor it over z, the integers, right? So here are 2 key hints. Take the 2, multiply it through this factor, because remember, if you want to factor over the integers, we don't like the 3/2. Bring the 2 in, and then you get a nicer factor. Also, you can factor t squared minus 4. All right, so a couple of key hints there. I'll save this. We can come back to this next time. Remember, you can factor that. Difference of 2 squares. Okay. Okay, questions? Questions?
On section 2.2, number 6, if I left my answer without an A coefficient, is that wrong?
Oh, no, it's not wrong, because I just asked for 1, right? But still, I put an A there just to show that you could have more possibilities.
Gotcha.
Right. But no, I just asked for 1. And if you get even 1, then that's good enough to solve the problem. Yeah. But it's a nice, yeah, it's a nice challenge to think about other possibilities.
2.3, number 4, I left it unsimplified. What would you prefer to see?
Well, at the very end, you mean when you get that final thing there?
Yeah, so I divided it and got an answer, and I didn't. The x cubed plus x squared minus x over x cubed minus 1.
Right. So let me 2, 3, number 4.
Yeah, I got the one in parentheses and left it as is.
Oh, okay. So technically, you should simplify this. Yeah. Now, granted, that's kind of rare for these long division problems because it's almost like a sneak attack. But it's true that if you have a common factor like x minus 1, as is the case here, you should simplify. So, yeah. And actually, this is a case where a student might look at my answer and go, "Oh, I didn't realize that simplifies." And then you go, "Okay, how do I do it?" So you factor out the x on the top, right? You get x and x minus 1. Down here, that's a difference of 2 nice cubes, right? So you factor that as a difference of 2 cubes. And it turns out that the x minus 1s cancel out. They divide out. So you're right. I would, officially, you should have this as your final answer.
Okay.
Because this is unsimplified. Although I couldn't blame students at all if they overlooked that. And if this were an exam problem, for example, I might hint at something. Psst. Make sure that your final thing is simplified.
Gotcha. And on number 5C, I didn't really understand. I just basically did synthetic division and.
Yeah, the idea is that so you put 4 in the dunk tank, right?
Mm-hmm.
You put the coefficients in the first row, and basically f of 4 is whatever you get as your final number here.
Mm-hmm.
Your remainder, right? So the remainder theorem says that you execute synthetic division, and then f of 4 just turns out to be whatever number you get here.
Gotcha.
Yeah, it's a nice, elegant way of evaluating functions. In fact, my calculus students really liked it because if you think about it, if you try to plug 4 into this and do it directly, a lot of students make a mistake, right, on their calculators. It's very easy to mess up on a calculator. Whereas here, bring down, multiply, add, for a lot of students, this is faster, more efficient, more accurate, even if they just use their brains, not a calculator.
And on 10B,
sorry. Yeah, this is your friend. It's meant to be an aid. Yeah. B here?
10B.
Oh, 10B.
On this section.
All right. Oh, yeah. Okay, so this is the one that people always ask about. I wonder if I have it's helpful to have my old copies here. Let me try to grab an old copy. Yeah, because I think I've worked this out earlier. I want to keep those notes. Zoom's making it look.
So what I did was, after doing synthetic division, the numbers on the bottom there, I just divided those all by 2 basically, except for the remainder, because I mean, it got me the right answer, but I don't know if that was the right move.
Okay, yeah, 10B. Yeah, I went over this with a student at one point. Yeah. So here's what's happening. So first, because we'd rather have something of this form, we factor two the leading coefficient out of the bottom, and the whole thing factors out as a 1/2, right? Not a 2, but a 1/2, right? So this divided by this, I'm rearranging that. You can factor out a 1/2, and then you get this, right? 1/2 times that ugly dividend on top divided by x plus 1/2. Okay. Did you get that observation here?
Instead, what I did is, for the d of x, I factored it out. So it was 2 and then open parentheses x plus 1/2.
Right.
And so I plugged in a negative 1/2 into synthetic division, and then all the numbers I got out of that, I just halved, except for the remainder. So the
Well,
6, the 2, and the
oh yeah,
negative 2
yeah,
I have.
yeah. So I'm explaining. So you're right, and you're wondering why it's correct. Okay, so here's the deal. So you put -1/2 in the dunk tank. You do that division, right? So the 1/2, that's not here, right? 1/2 times, and then from your third row, 6x squared plus 2x minus 2 plus this fraction, right? The 1/2 distributes. That's why you take half, right? The half distributes. You get 3x squared plus 1x minus 1 plus, and then when the 2 here hits that denominator there, it reverts back to 2x plus 1.
Mm,
The 5 stays intact, as you noted.
got it. I see now. Thank you.
Oh, yes, and yeah, and every conscientious student who makes it this far in the homework, they always ask about this one. But it basically demonstrates to you a hack that allows you to use synthetic division even if the leading coefficient is not 1. So this is the hack.
And 11C is also the same thing, just synthetic division to demonstrate the remainder.
Correct.
Okay.
And I suppose that's a 0, I hope, because then that'll help you answer the rest. So if I'm being nice, then 3 is a 0. You should get 0 as a remainder. Is that right?
Yes.
Yeah, that's right. That's right. 0
I
remainder.
just got confused since B was also asking for synthetic division.
Yeah, so see, there's basically no additional work. You just identify. You
Okay,
identify
got it.
F3 as the remainder, as that guy in that last box here. I'll put a check mark. Yeah. So
Okay.
part C was just a recognition problem.
Hmm.
Basically, if you show me the work for B, you don't have to show me further work. You can just grab whatever, I guess 0, right? And then yeah, 0, right.
Got it. Thanks. I see a question in the chat, so I don't want to hog time here.
Well, let's see, 2514C. All right, so what's going on here? So list the possible rational zeros. I give a key hint in B, right? So -2.
I use that one, -2, and use synthetic division.
Right, so you get this that division, right?
Yeah, I
4.
get a 5, -4.
-4, 8, okay. So bring down the 4, -8, add, you get 5. Multiply, you get -10.
Yes, -10 and -4 after that.
-4, +8,
Yes,
+4, oops, +4,
yes.
-8, and then 0 finally. Good. All right. So use synthetic division factor. Okay, so when you factor this thing, okay, so you're going to get the, okay. Oh, -2 is a 0. So what's a factor? R.
That I didn't understand.
Okay, -2 is a 0, right? Because h of -2 is 0, right? We have 0 here, right? So -2 is a 0. Right. Okay. So h of -2 is 0. This is telling us by the remainder theorem, h of -2 is 0. Okay, that means -2 is a 0 of h.
Right.
Okay.
Do we factor after this one? Can we factor again 4, 5, -4? That
So here's what you do. If -2 is a 0, r plus 2 is a factor, right?
yes.
4th degree divided by 1st degree is 3rd degree. You get a
Right.
3rd degree from here, right? So we have 4 r cubed plus 5r squared minus 4r plus 4. And I can understand if you feel kind of frustrated, you're going, oh my gosh, how do I do that? But remember my hint, -2 is a 0 of multiplicity 2. That's
That's why I didn't understand that multiplicity.
okay, so here's the deal. See this 3rd degree guy?
Yes.
What I'm saying is that -2 is going to work again. It's going to work again. If you put
For the second. Ah,
-2 in the dunk tank, and if you take the coefficients from this,
ah.
the 4, 5, so basically you put this as your first row, and you repeat the process. That's going to help you.
All right, I see now. That's why I didn't understand the
Right. That's critical because see, otherwise you're going, oh my gosh, do I have to check and guess? No. A key hint: -2 is going to work twice. It's going.
Now I
That's
see.
what the multiplicity means here.
Okay, excellent. Now I see.
Yes, you're very welcome. Yes. So go ahead and keep playing with this and see if you match my answer.
Great. Thank you.
You're welcome. Yes. In the meantime, any questions in the meantime? Any questions?
That's it for me.
Any questions?
2.5, number 4, please. I was unable to complete
Okay,
it.
2.5,
Yes.
number 4. Ah, x cubed plus 5. You want to factor. What's the idea? Treat this like a sum of 2 cubes. I realize 5 is not a perfect cube, but we can work it. Okay, so it's SOAP. It's SOAP. All right. Let's see. Where do I? I'm running out of space. Okay, so okay, so we're looking at 254. All right. Okay, factoring x cubed plus 5. All right. GCF is 1, by the way, right? Okay, so we're going to treat this as a sum of 2 cubes. And it's going to factor as a binomial times a trinomial. The signs follow the SOAP pattern, S-O-A-P. All right. The cube of what is x cubed? It's x. Same sign, plus sign. Now 5 is the cube of what number? It's not very good looking, but 5 is the cube of what number?
Cube root 5.
The cube root of 5, correct. Which is a real number, and you're allowed to factor over the reals now, right? In general. Now let's build up the trinomial, all right? The square of x is x squared. O stands for what?
Opposite sign.
Opposite, so what goes here?
Minus.
Minus, whether you look at here or here, right? And then you take the straight product. Okay, so I'll put the cube root of 5 in parentheses here. There are lots of ways to miswrite this, but cube root of 5 times x, all right, that's the straight product. AP, what does AP mean?
Always positive.
Always positive or always plus. And then you take the square of this guy here. There are different ways you can write it. One way you can write it is that it is the cube root of 25, because remember, you can tuck the square in there. This is the cube root of 25. And some books might leave it like that. Some people might put 5 to the 2/3. I'll take that also. All right. So there are a variety of different formats, and I think it's instructive to realize that there are different formats you could use. That should be the answer. Let me check here. Wait. Oh, yeah. I'm looking at the wrong number. This is 4. It's number 4 on 2.5. Yeah. So x plus the cube root of 5, and then x squared minus the cube root of 5 times x plus the cube root of 25. Right. I guess I just wrote that form. That's the most natural form. Right.
Awesome.
Right. Right. That's correct. It's following the template of the sum of 2 cubes. That is correct. Yes. Okay. Anything else?
On number 9 of this section,
Okay.
why is it considered complex zeros? The two.
Oh yeah, because these are complex numbers. They just happen to be real and integer, right? And bear in mind, sometimes on exams, I ask people, given the complex zeros, and the solutions happen to be, real or integer even. Yeah.
Got it.
What's this 9? So maybe it's just a matter of people recognizing that, hey, 0 is a complex number, right? All integers are complex numbers. You know that Venn diagram? C is the biggest set, but it also includes all these intercepts. Okay, so if you get 0, that's a complex number. If you get 3, that's a complex number. If anything, I'm being a little mean in using the word complex because you're thinking, oh, it's got to be 2 plus 3i or something. Not necessarily. It could be 0. It could be 3. Right. The harder part is factoring.
And on number 12, why are there no zeros? Like, not zeros, but like, why is 0 not a real coefficient?
How many real zeros on number 12? How many
Yeah, it
real
starts at 1 instead of 0, like the even function.
Right. How many real zeros can a 9-degree polynomial with only real coefficients have? And you're asking how many distinct real zeros?
Well, I originally wrote my answer 0, 1, 3, 5, 7, 9 because in number 11 there were the 0 included in.
But here, think about the graph. Think about the graph. If you have a 9-degree polynomial, what does the graph look like in the long run? Odd degree. What is an
L to
odd degree?
heaven.
Sorry?
L to heaven.
Yeah, snake. I call it a snake graph. Yeah, sure. Now, tell me, if you have a 9-degree polynomial graph, true or false, there must be an x-intercept.
Yes.
True. True. Therefore, there has to be at least one real zero, correct?
Yes.
Yes. So 1 through 9, no 0.
Oh, okay, that makes sense now.
But
Okay.
that graph, see, it's kind of tricky because that graphical intuition sneaks in there. I like these problems as pedagogical tools. I mean, they're great to have people think through things. Yeah. But of course, on an exam, I wouldn't put like 10 of these because that'd be very stressful. But these are good to get you thinking about the underlying theory and the graphs.
Got it. Thanks.
Yes, you're welcome. Yes. Okay. It's 10 p.m., but I'll go on. Okay, so I'll wait another minute for anything you may have now. Otherwise, at the end of the minute, I'll take a 5-minute pause as people think.
Is the solution for number 13 here on
Are you
YouTube?
talking about this one? 13 here?
Was this done tonight or is this on
2.5.
YouTube?
2.5, right?
Yeah.
Did I do this on YouTube? I may have. Yeah, if I worked this out in a previous class, maybe. I should probably keep track of which ones I've already done. That's okay. Oh, now tonight, by the way, we're still recording, right?
Yeah.
So tonight will be on YouTube.
Okay.
Yeah, barring a glitch. Is that what you were asking? If tonight will be on YouTube?
Oh, on number 13, so you don't have to go over it again. If 13
Right.
is
So
somewhere on.
the work I've done here, I'll record, and as long as there's no glitch, it'll be on YouTube. Yeah.
Okay.
Okay. There are other pieces, but I'll leave that to you for now, and then we can go over that. Yeah. Okay. Any questions? Again, after the at 10:03, I'll pause for 5 minutes and see if anyone, if as you gather your thoughts. And I'll remind myself to record. Yeah, because students appreciate the videos. Okay, any questions? Otherwise, I'll pause for 5 minutes. I'll come back at 10:08. So at 10:08, I will return. Okay. In the meantime, go ahead and see if there are any more that you wanted to kind of mull over things, right? I'll be back at 10:08 then, right? I'll pause. All right, I am back. Any thoughts? Any questions?
I'm actually good for now. Thank you, Professor.
Yes, have a good night. Thank you for your commitment and your hard work. Thank you. I'll see you soon.
Thank you. Take care.
Take care.